Hi, welcome to uh, analysis of this CS amplifier. Of course, we know that this is the CS amplifier with biasing circuit, which is provided using R1, R2, and of course VDD is the supply voltage, RD is the resistor across which the output voltage will drop, and this is the input voltage coupling capacitor. So this is the output AC voltage we are talking about, and at the same terminal we're going to have a DC voltage which is given by VD now. So let us write the AC equivalent circuit of this actual circuit. So as per the thumb rule, we will going to short this capacitor CC over here, and this VDD is AC grounded. So this is now AC ground. So this is AC ground. So now we are replacing this transistor by its small signal AC equivalent circuit. Now between gate and source, it's an open circuit having a voltage plus or minus VGS here, and between drain and source, so there's a current source having magnitude GM into VGS. And of course this RD is connected from drain to AC ground, this one, and here where the output voltage is measured with respect to ground. The same thing can be rewritten over here like this. So now this R1, R2 are coming parallel here. So this is GM into VGS and this is RD. So we can write the expression for the output voltage as, okay, now this is minus GM into RD multiplied by V in, because whatever VGS is there is equal to V in here. So this is actually VGS between gate and source. And from this first circuit diagram, we can write VD, the voltage at drain point is given by VDD minus ID into RD. Now let us see how do I increase the gain of the amplifier, because when we say an amplifier, so we always tend to have gain more and more. So if you can see this expression where V0 is given by this, so I can rewrite the expression for gain as AV is nothing but V0 by V in. Okay, let me write it here. AV is nothing but V0 by V in, which happens to be minus GM into RD. So we know that this negative sign is so seen at the output voltage as out of phase signal compared to input. GM is the transconductance and RD is this resistance. Suppose if I want to increase this AV, there are two possibilities. I should either increase the value of RD keeping this GM constant, or keep this constant, vary this. So let us see what happens if I vary the value of RD. So naturally, if I change the value of RD, AV will certainly increase. If you can see here, so this is the voltage VD. So let us try to understand what is this VD means over here in output time response. So assume that this is your output swing available. This is 0 and this is VDD, and we know that we need to keep this MOSFET in saturation for all the time to operate it as an amplifier. So this I'm dedicating it to keep it in saturation. So this voltage we call it as VOV. So that is overdrive voltage, which is nothing but VDS sat. Now, so I want to, of course, suppose if you assume that this is 0 volt and if it is 1.8 volt, the ideal value will be somewhere here. Suppose if you assume that this is around 0.2 volts. So how much is left out now? The left out voltage is 1.6. So 1.6 means half of, from here to here it is 1.6. Half of 1.6, 0.8. 0.8 from the top happens to be 1 volt. So this is, from here it is 0.8. So from here it is 0.8. So my VD should be 1 volt to have okay, of course from here to it is 1.6, so that this voltage is, so VD, if VD is equal to 1 volt, I can effectively utilize the swing. Assume that I'm having a signal. So here assume that I don't apply the signal. If I apply the signal after some time, if I apply the input voltage, if this is my V in, how does my V out will look like? So my V out will be till this point the output voltage is at at 1 volt. As the input voltage increases, output will decrease and it will have something like this. So this is my output voltage. Now assume that you increase the value of RD. Of course, we will get, this is V in, this is V naught, we'll get a gain of some value. Suppose if you increase the value of RD, certainly the gain will increase. More than that, can you see this RD will increase this ID into RD, which will reduce my VD value. So VD was actually 1 volt. Now VD will reduce to some lesser voltage. Now we can see it has reduced to a lower voltage. Now it has reduced to a lower voltage. Now it will try to swing. So when it tries to swing, can you see this is coming sooner and it may go till here top, but here it is an issue. So if you increase the value of RD, as VD is keep reducing. So assume that this was 1, this has become 0.6. When it is 0.6, how much is the swing that you have at the bottom? You hardly have 0.4 volts. If you further increase, this may come down. So the value of RD will certainly reduce, or the increased value of RD will reduce the value of VD, so that I will left out with very less swing at the negative, at the lower part of the output waveform. So increasing RD to a greater value has an impact on the output swing. So it's not a good practice to increase the value of RD to have a larger gain, or it's impossible to get a larger gain with this resistive load, because if you have a resistive load we know that as the drop across this is increasing, this VDs keep going down. So this VDs keep going down, so which will going to harm my voltage swing. So then we have to find out some resistor which should offer very high resistance but should not consume too much of voltage drop. So as you can see here, if this voltage drop is more and more, if this voltage drop is more and more, I will have lesser and lesser VD, which will going to reduce my swing. So what is the option now? I have to use some different component or some different thing which will have a large R but less voltage drop across that. It should have a less voltage drop, that is whatever, okay, let me write as VRD. So VRD should be as small as possible. So let us see how can we achieve that. So now what I'll do is we'll just think of something like this now. So now before we actually go into the circuit, let us consider what happens to okay, now let us do one more thing here. So far we have considered lambda as a zero quantity. Since lambda is 0, R0 happens to be infinite, so that's why we didn't represent any R0 here. Suppose if this lambda becomes non-zero, then R0 is non-infinity, so I have to represent a resistor R0 now. So this is what the resistance associated with the current source of the op amp, of the MOSFET. Now I will represent this also over here. So this is my R0. So what's my equation of gain becomes? So gain equation will become minus GM into RD parallel R0 is my AV. So this is my AV. So instead of having only RD, I will have R0 also coming into picture, because this parallel combination is nothing but R not in parallel with RD. Okay, what is this now? This is a MOSFET having channel length modulation. When I say channel length modulation, we know that MOSFETs have a output characteristics, which is VDS, this is ID for a given VGS. So this is an ideal MOSFET. So where this is VGS, so this is not at all changing over the entire length. So this is saturation region, and here for this lambda is 0. So we know that typically in a practical MOSFET, actually the current increases. So this is now lambda is non-zero. So typically the value of lambda is either 0.1, lambda is 0.05 or 0.01. These are the typical values of lambda whose unit is volt inverse. So this is volt inverse. The associated equation for this if you consider lambda is ID is given by, in case of saturation, it is half Kp W by L. It is VGS minus VTO whole square 1 plus lambda VDS. Lambda VDS. This is VDS, this is VGS. So this is the expression for the drain current under saturation region with lambda non-zero. By considering, okay, when I say lambda non-zero means you are considering channel length modulation. Channel length modulation is considered. Now let us consider a MOSFET having lambda non-zero. Let us try to see what is the resistance offered by this MOSFET if I look from drain side. I know that this is source, this is drain, this is gate. So let me just do it like this. Let me have a DC source here. Assume that this is a part of a circuit. So this is having certain VGS where it is going to turn on the MOSFET, and it will keep the MOSFET in saturation also. If the MOSFET in saturation, I want to know what is the resistance seen towards the drain side, So for that, what I'll do is I will connect a dummy source of magnitude Vx. Now I want to measure RAC, that is AC resistance looking into the drain. So why it is AC resistance? Because I want to use this MOSFET for my AC analysis. So I want to see what is the resistance seen by an AC signal. For that, I'm having a AC input, AC voltage Vx. I will measure the current Ix. So what is this resistance R, which is a AC resistance looking into the drain? Looking into the drain is nothing but Vx by Ix. It's not possible to have a multimeter and measure the resistance which is looking into the drain. So it's not possible. Only way to measure that is you apply some dummy voltage and try to measure what is the current that is going into the circuit. The ratio of Vx by Ix happens to be the resistance looking towards the drain side. That's the AC resistance. Now let us see how do we do that. So we know that whenever you consider AC resistance, or whenever you consider AC analysis, all DC voltages are grounded. So I'll ground this. So I have grounded the gate. Source is anyhow grounded. Now I will apply the source, that is Vx. This is Ix. Now let me replace this MOSFET by its AC equivalent. So what is the AC equivalent of that? We know that this is gate, source. Between drain and source, I have Gm into VGS. Since lambda is non-zero here, I will have R0 also coming to picture. So let me rewrite it here. So this is my Gm into VGS. This is R0. R0 is what? This is the resistance associated with the MOSFET. This is a small signal model, and this is my Vx. This is Ix. And we know that this is gate. Is the gate grounded? Okay, let me just discard this. Is the gate grounded? I am grounding this. So gate is actually AC grounded. AC grounded, and this source is the actual ground. This is source, gate, drain. This is plus minus VGS. So what is VGS now? Is this not VGS? So is VGS is equal to 0? Then what is Gm into VGS? Is this also 0? Then how do you, is this a current source? So this is actually a current source. If current source is 0, I need to represent it using a open circuit. So let me open circuit this. Let me rewrite this now. This is grounded. This is also anyhow grounded. So this is now open circuited. This is now R0, and I have this plus minus. This is Ix. This is Vx. Then what is Ix is equal to? Ix is the current that is going into the resistor, the voltage is Vx. So shall I now write Ix is equal to Vx by resistance R0. This R0 is associated with the MOSFET, which is the resistance R0. So now what is Vx by Ix? Can I write Vx by Ix, which is now given by R0, meaning for a circuit in which gate and the source, if these two are AC grounded, if you look towards the drain of any MOSFET, the resistance seen is R0. The resistance seen is R0. So this is true. Of course, we took NMOS transistor and then analyzed that. Okay, it is equal to R0. That is looking towards the drain. It is R0. This is true for even PMOS also. Even for PMOS transistor, if you are looking towards drain. So let me write that. How do I write it? So let me consider this PMOS transistor. This is my PMOS transistor with the source here. Now, if I AC ground this, if I AC ground this, if I look towards the drain, the resistance is R0. The resistance is R0. So what is the magnitude of this R0? Because we know that R0 is given by 1 over ID into lambda, where ID is the current flowing through the DC current flowing through the MOSFET, and lambda is the channel length modulation factor. On the same lines, suppose if you have again same NMOS transistor. Now this is source. You look towards the source, find out what is the AC resistance provided. This is AC grounded, this is also AC grounded. If gate and drain are AC grounded, what is the resistance of this MOSFET looking into the source? What is AC resistance looking into the source? So for that, let us again do the same analysis. So what do I do? Let me connect a dummy source. I'll connect a dummy source. Here this is Vx. I will measure what is Ix. So is this Vx by Ix happens to be the resistance AC signal looking towards the source? I can actually find out what is the distance. So let us rewrite this. So is this gate now? Is this source? Is this now Gm into Vgs? And since lambda is non-zero, whenever we consider finding our AC resistance, let us always take a typical MOSFET with lambda non-zero. That is, we will have R0 also in the small signal model. So is this AC grounded? This is also AC grounded. This is also AC grounded. This is plus minus VGS. So am I applying a Vx at the source side? Yes, this is my Vx. This is Ix. This is Ix. So now I want to get the expression for Vx by Ix. That will be my resistance. That will be my AC resistance looking towards the source side. So of course, this is drain. So now let us consider this as node A. Let us try to write a KCL at node A. So let us consider this current as IR0. This current is known, so this current is Ix. So to this node are all the currents entering that node. So shall I write Ix plus Gm into VGS plus IR0 equal to 0. So IR0 is the current flowing through this R0 resistor with this at higher potential, this at lower potential. Let us write. So this is Ix. If you see carefully, this is Vx plus this is minus negative term. Is this minus grounded and this plus of Vg is also grounded? So I can write as per this Vgs is equal to minus Vx, because these two are exactly opposite. Plus is connected to minus, minus is connected to plus of Vgs. So Vgs is equal to minus Vx. I can write it as minus Gm into Vx. What is this current IR0 flowing here? is the potential 0 here at one end of R0? What are the other potential? Is it not Vx? It is 0 minus Vx by R0 is equal to 0. So can I now write Ix equals Gm plus 1 over R0 into Vx? So I can write it as so. So now I will rewrite this as Vx by Ix is equal to, is it not 1 over Gm plus 1 over R0? So this is my R out. This is my RAC looking towards source. So if I look towards source, the resistance is 1 over Gm plus 1 over R0. So of course this is the entire value. If you can carefully see this, so this 1 over Gm plus 1 over R0 is actually like having these two resistors in parallel. Assume that this resistor is of value R0, this resistance is of value 1 over Gm. Can we actually find out what is the resistance of this parallel combination? So is it not, can I write, suppose now let us take a general case. So let us take a general case where you have this as R1, this as R2. So what is R equivalent here? R equivalent, is it not R1 R2 by R1 plus R2? Can we also write this in another form as 1 over R1 plus 1 over R2? I can write this way also. Now let us assume that, can you see these two circuits are almost same? Shall I name it as 1 over Gm? Shall I name it as R0? Now let us replace what is R1 now. So it is now 1 over, what is R1? R1 is actually 1 over Gm. So what is R2? Plus 1 over R2 is R0. So now can I write this as what? So this is now, because it is 1 over Gm, can I write it as Gm plus 1 over R0? So what is actually this? So is it not 1 over Gm parallel with R0? Meaning whatever equation you have here is nothing but 1 over Gm in parallel with R0. This is the resistance looking into the source for an AC analysis. What is the condition? The condition is gate and drain should be AC grounded. AC grounded. If these two are AC grounded, you will have this. As we saw here, this is AC grounded, this is also AC grounded. If you look towards source, the resistance is 1 over Gm parallel R0. In the previous case, we saw that when gate is AC grounded, source is AC grounded, looking into the drain, it was R0. It was R0. Let us take the third case where we have a slightly different case. Now let us again take drain, but let us make gate and drain shorted. Let us make this AC grounded. See, now this is not AC grounded, but in turn it's connected to drain. So I want to see what is the resistance. I want to see what is the resistance looking into the drain, but here the condition is gate and drain are shorted. So what is the condition? What is the procedure? Let me apply a dummy source Vx of known amplitude. Find out what is Ix. So what I'll do, I will write the small signal AC equivalent circuit. So what is the small signal AC equivalent circuit? It is gate, source, between drain and source I have Gm into VGS, and of course R0 is also there because I'm considering lambda as non-zero. And where is this Vx applied? Is it not applied here? Is it not Vx? Am I trying to find Ix now? Correct. Is this grounded? This is grounded. How about this? This is not grounded now. You can see gate is shorted with drain. Shall I short this and this? This is plus minus VGS. See now, this is that extra connection because of this, so it is now so on. Now, what is, shall we now find what is IX? Again, to this node A. To this node A, write KCL at node A. So what is one of the current entering? The current entering is IX. Let us assume that this is one current which is flowing, which is leaving that node. Let us name it as IR0. The other current is this. Shall I write the incoming current to this node is IX. The outgoing currents are IR0 plus GM into VGS. So do you agree that, okay, how about this current? Is any current going here? So this current is actually 0. Why? This is open circuit. Now, if you can carefully see this, is this point same as this point? So what are the voltage here? Do you have Vx here? So now from the circuit, can I write VGS is equal to Vx? Can you see this? This entire Vx is going here. So this is VGS is exactly equal to Vx. So now let me rewrite that. Ix is equal to, then what is IR0? IR0, is it not Vx by R0? Because this is Vx, this is 0 potential, so Vx by R0. Vx by R0 plus Gm into Vx, because this VGS is now Vx. So can I now write Ix is equal to 1 over R0 plus Gm into Vx. So what is Vx by Ix? Is it not 1 over R0 plus Gm? Oh, what is this? Now when you are looking into the drain with gate and source AC grounded, the resistance was R0. Now you are again looking into the drain with source AC grounded, but the gate is connected to drain. The resistance is now, so do you know, okay, as we saw in the previous case, are these two resistances same? Are these two expressions same? Can you see it is same? It is 1 over Gm plus 1 over R0. Is this not equal to 1 over Gm parallel to R0? So now if you are looking into the drain, if the drain and gate are shorted, the resistance is 1 over Gm parallel to R0. Suppose if I take out this and then make AC ground of this, so then it will become R0. So we have seen three different categories. So let us summarize this. In a particular circuit, let us write all 6 combinations of N and PMOS transistor. Let me write all 6 combinations. This is NMOS, NMOS, NMOS. So this is now PMOS, PMOS, PMOS. Now if I AC ground this, the resistance looking into the drain is R0. Now let me AC ground this. So because we know that this is gate, drain, source. This is again drain, gate, source. If I ground this drain, if I look into the source, the resistance is 1 over Gm parallel R0. Come to this. You have, of course, what is third category? Third category, you had it like this. Gate and drain are shorted. If this source is AC grounded, the resistance looking into the same drain is 1 over Gm parallel to R0. It is 1 over Gm parallel to R0. Now, See now, did we look into drain? Now in PMOS also let me look into drain. Because source is at higher potential, I wrote it here. If these two are AC grounded, if these two are AC grounded, the resistance seen, because it is drain it was R0. And you see towards the source, you ground this, you ground this. So what are the resistance looking into the source with gate and drain AC grounded? It is 1 over GM parallel to R0. Now let us consider the third case where gate is shorted to drain. This is AC grounded. If you look into the drain, it will be 1 over GM parallel to R. These are the three categories of MOSFET which are offering now the resistance. Now we had this difficulty, we had the difficulty of having larger resistance to get more gain, but this was consuming too much voltage. Now if you ask, sir, what is the value of R0? How much does this is consuming in terms of voltage? Suppose assume that if ID flowing through this MOSFET is 1 milliampere, if the value of lambda is 0.01, if it is 0.01, then what is R0 of that? Is it not 1 over ID into lambda, which is nothing but 1 over 1 milliampere into 0.01 volt inverse? Is it not 100 kilo ohm? See now, this MOSFET will give me a resistance of 100 kilo ohm, which was very difficult to achieve here. Of course, even you can connect 100 kilo ohm and then 100 kilo ohm, you can connect a 100 kilo ohm resistor, but what happens to this VD? This will become so large so that VD becomes negative. So it is not possible to have a passive resistor of 100K, but you can use this MOSFET which will offer you 100K. How much the voltage does this require? Does this require too much voltage? No. If the overdrive voltage, if VDS sat for this MOSFET is 0.2 volt, then this requires to have only 0.2 volts to give 100K. See now, the problem of now the requirement of large resistance but lesser drop, did we achieve it using this type of configuration? Is it not offering very large resistance? Is it not consuming very small voltage? So this type of configuration where it offers resistance but consumes less voltage is known as active loads. So this is, all these are active loads. Active loads. Now let us take one by one, try to find out what is the resistance offered by each one of them. Let me just, I think it may not be difficult if I just, let me just do it. So let me take the first load, again CS amplifier. I will take what I'll assume is, so we will assume that there is a proper biasing done. So now let me apply the input voltage here. This is my output voltage measured point, and here this is my transistor M1, source grounded. So this is my another transistor where I'm applying some bias voltage VB. So here this Vin also has a VB. This Vin, just Vin is not sufficient, I should bias this also. So this is where I am applying the input voltage plus the DC. Here only DC. Here there's a DC voltage. So there's a PMOS transistor. Let us name it as M2, because usually in SPICE programming the MOSFETs will be identified by M1, M2, M3. So let us assume that they have non-zero lambda. So they have some resistance. Associated with that MOSFET. Now, how do I write its AC equivalent circuit in the first go? Shall I replace this by a ground? Shall I replace this also by a ground? Because those two are only DC voltages. because you had some VB. Suppose if I say this VB1, VB2, even though there is a bias voltage here, suppose if I write its AC equivalent, so shall I now write it this way? So even though you are grounding this, but do you have this input voltage still existing? This is my output voltage. Shall I now ground this AC ground? Can you see this DC voltage? I'm grounding it. Can you see this is also one more DC voltage? I'll ground this. This is AC ground. This is AC ground. This is also AC ground. This is my source. This is source. This I'm grounding, actually grounding. So this is M1. This is M2. So now, is this transistor which you're considering this way, is it not of this type? See here, are these two are of same category? See, is gate grounded? Is source grounded? Now, are you now looking for a resistance offered by this, offered by M2? So what does this M2 will offer now? Does M2 offers R0 now? So now, if I want to understand, or if I want to analyze the AC analysis of this circuit, instead of having this complicated MOSFET, these two grounds, shall I replace it by a simple resistor by R02? Because this is in general R0, because it is simply M. So if I write it as M3, so then this is R0. This is R0. So since I'm naming it as M2, this is R02. Can you see, is this grounded? So now, shall I write it this way now? V in ground, this is my V naught. So now, this complicated circuit has reduced to this very simple circuit. Now, what is its AC equivalent? Now, shall I replace this by its small signal model? What is the small signal model of this one? Is it not this? GM into VGS. Shall I write it as GM1 into VGS because it is M1? What is this? Does it has a resistance associated with as R01? Because this is lambda non-zero. Here lambda is non-zero. There is associated R0. So let us name it as let us name the resistance associated with this as R0. Do I have a R02 also connected to AC ground? So this is anyhow ground. So shall I connect R02 here? So this was my V0, this is my V0. So what is V0 expression? So of course you have the input voltage here. This is gate, drain, source. Shall I have the input here? This is Vin, this is plus minus VGS. So what is V0? Is it not minus GM1 into R01 parallel R02 into Vin? Now earlier you had a resistance of 1K. Earlier you had a resistance of hardly 1K. Suppose if it was 1K. Now what was the gain? It was GM into RD parallel R0. This was still less than 1K. Now you can see if it is 100K, if R01 is 100K, if R02 is also 100K, do you now, of course in the previous case, if it is a resistive load, did you have it as minus GM1 R01 parallel RD? Even though R0 is 100K and RD is equal to 1 kilo ohm, can you see it is minus GM into, assume that GM is actually 5. Assume that GM1 is equal to 5 millisiemens. So what is GM1 into 100K in parallel with 1K? Can we find what is 100K in parallel with 1K? If I actually find 100K in parallel with 1K, so how do I do that? It's very simple. So it is 100 inverse plus 1 inverse equals whole inverse is 0.99K. That is, this parallel combination is 0.990 kilo ohms into assume that this is minus 5 milli. This milli and that will go, is it not, into 5? Do I have a gain of minus 4.95? This is the gain if you had a passive resistor. Now when you are having an active resistor, what is the possible gain? Can you see, is it still minus 5? Is this 100k? Assume that this is also 100k. Does it give 50k? Because now it is 100k in parallel with 100k will give you 50k. Is it not minus 5 into 50k? Of course, minus 5 millisiemens. This is millisiemens. Does this milli and k will go? What is 5 into 50? Is it not minus 250 is the gain? So this is with active load, this is with resistive load. So if you have a MOSFET, if you have a CS amplifier with active load, now what is this role of this one now? The role of this is RD. RD, whatever you had it in the previous circuit. In the previous circuit, what is this? This is actually playing the role of RD. But what is that value? That value is R02. That will be a huge value. You can still achieve a very large resistance using a smaller voltage drop. So your gain can increase enormously. So that is the beauty of this active loads. Now we have considered looking into the drain. Let us have the same circuit, put a NMOS transistor. Let us see what happens to gain. Let me just do this again. So let me have next circuit where I have load is also NMOS, this active is also NMOS. So this is M1 where I'm applying the input voltage. This is my load MOSFET, this is my VDD. Let us assume that this is also NMOS. In the previous case we had it as a PMOS, now this is NMOS. Can you see the arrow mark here going into this? So this is actually PMOS. This is PMOS. Here this was NMOS. This was NMOS. Now here both are NMOS. This is also NMOS. This is also NMOS. Now shall we write its, of course this is my V0. Shall I write its AC equivalent? So we know that as per the thumb rule, let me ground the DC, AC grounded. Let me AC ground this. Now this is my circuit. This is V in, this is V0, so on. So M1, M2. Now do we have a condition where gate and drain are shorted? You are looking into the source. Do you have something like this? See here, do you have similar situation? Let me see here. Is this situation you have? Just have a look here. Is the gate grounded? Is the gate grounded? Is the drain grounded? Are you looking into the source? Are you looking into the source? What is the resistance? It is looking into this is 1 over GM parallel to R. Now can I rewrite this as V in, this is ground, this is this. Is this AC ground? Is it not 1 over GM parallel with R0? So shall I do it as 1 over GM to R02? Because this is M2 resistor. So what is this? This is M1. This is M1. Correct? Now when we actually wrote, of course I can write a small signal model of this one. So only difference between this circuit and this circuit is we have simply replaced. So what is the difference between these two? The difference between these two circuits is here you had a PMOS transistor looking into drain. Here you have a NMOS transistor looking into source. See, now everything is same, but here the resistance is R02, but here resistance is 1 over GM2 R02. So this was my small signal model with this as R0. So what is the small signal model of this with this as 1 over GM2 R02? So shall I, of course, instead of rewriting it, shall I replace this by 1 over GM2 parallel R02? This resistance will simply change from R02 to this value, Then what is this effective resistance? So shall I write now V0 is equal to minus GM1 into V in. What is the resistance? It is R01 parallel with R02 in parallel 1 over GM2. This is R01. What is this resistance? It's 1 over GM2 parallel R0, 1 over GM2 parallel. So we know that this GM, suppose if it is 5 millisiemens, do you know what is 1 over 5 millisiemens? Is it not 5 exponential minus 3? 1 over that is hardly 200 ohms. This is 200 ohms. So this is 200 ohms in parallel with 100k, and that whole parallel with 100k. So you have something like this. V0 is equal to, okay, V0 by V in is equal to minus GM1 100k in parallel with 100k in parallel with 200 ohm. So shall we do that? It is 200 ohm plus 100 exponential 3 inverse equals whole inverse is 199 ohm. So this entire thing is 199. This entire thing is 199 ohm. Do you know now 199 ohm into 100k, is it still again like 199? What is this 199? Is it not 1 over GM2? So now can I write this entire expression as V0 by V in? Okay, let me just rewrite it here. So let me write the AC small signal model of this now. This was GM1 into VGS. This is plus minus VGS. This is V in. This was R01. The resistance looking towards the source is R02 parallel 1 over GM2, which is approximately equal to 1 over GM2. Now, so what is V0 by V now? It is GM1 into R01 parallel 1 over GM2 parallel R02. Since this parallel combination is almost close to 1 over GM2, again this is in parallel with, this is, just put this R01, again GM1. So what is the parallel combination of these two? Since it is very small, is this value is again GM1 multiplied by, does this reduce us to 1 over GM2? This reduces to 1 over GM2. Of course this is minus, minus, minus. Is it not minus GM1 by GM2? If GM1 is equal to GM2, is the gain of this becomes minus 1? See what the difference, what I'm trying to say is when you had R0 as the load, the gain was almost minus 250. The moment you have source as a PMOS transistor with source as the resistance seen into that, which is 1 over GM parallel with R0, the gain becomes almost close to 1. So this way, depending on what is your load resistance, whether it is R0 or no GM, the resistance will change. Now this entire thing, suppose if I'm replacing this by something like this, you tell me what is the gain. If it is V in, if I do it like this, this is VDD, this is ground, this is V0, assume that this is my PMOS transistor, it is this. So can you tell me if this is M1, if this is M2, can you tell me what is the resistance looking into the drain now? Is the resistance looking into the drain upward, is it not 1 over GM parallel with R0? 1 over GM2, can I replace it by a resistor something like this? V in, this is M1, is it not a resistor of value 1 over GM2 parallel R02, is this AC grounded? then what is V0 by Vin? Is it not equal to Gm multiplied by R01 parallel to 1 over Gm2 parallel to R02 as in the previous case? So even though you have a PMOS transistor, since its gate and drain are shorted, the resistance is 1 over Gm in parallel with R0. Since it is M2, we are writing it as 1 over Gm2 R02. So here also the AV is almost equal to -1 provided Gm1 is equal to Gm2. Gm1 is equal to Gm. So this way we can able to use the loads effectively to get different gains. So this is active load. Either you can have it in this configuration, this or this. So any of the configuration. Okay, thank you.